Yes. Very excited. 4 o'clock. Let's go and get started. All right. Good afternoon, everyone. How's everyone doing today? Doing good. Doing good. After the midterm, I haven't looked at the midterms yet, so I don't know how everyone's feeling. But how's everyone feeling after the midterm? I'm good. Okay. All right. It's good. It's good. And so I'm hoping to get them graded by Thursday. And so actually today I'm going to stay a bit late just so I can knock out all the other stuff I need to do this week, so I can just focus on it tomorrow and maybe Thursday morning. And so hopefully you should know what you got on the midterm by Thursday. I usually don't like to keep those more than a week. And so I know quite a lot of people are on Zoom today, and so if you want to come to class on Thursday, you can expect the midterms to be graded by then. So you can pick them up on Thursday. Okay. And so today, we're going to be doing we're going to be kind of making a big shift in this class. And so, we're going to be moving away from biostatics, and from now on until basically the end of class, we're going to be working on biodynamics. Okay. And so we've already examined, the body and static positions. And, I think that's a good place to start, just because it really introduced us to a lot of important concepts in biomechanics, things like muscles, things like moment arms. We talked a lot about the tissue mechanics as well. And so now I think we're ready to start the discussion of human motion. Okay. And so, this second half of the class, I think, mathematically and conceptually, it is a little bit more intense than the first half of the class, but it's going to build on a lot of the stuff that we've learned already. And so, for an example, this week we're going to talk about gait, which is basically walking and running. Okay. And then next week, we're going to actually revisit muscles and talk a bit more in depth about that. Okay. So a lot of what we covered now is going to build what we've done before, kind of, at an increased level. Okay. All right. And so another announcement I have is that homework 4 is posted online. And so you'll have that available. I'm giving you guys a little bit over 2 weeks to do them, because homework 4 is a bit time consuming. And so make sure you give yourself enough time to do that. And so the subjects for homework 4 are going to be what we cover this week in gait biomechanics, and then what we cover next week in muscle dynamics. Okay, so if you looked at the homework right now, you probably have no idea where to start. But as we kind of go through the next couple of weeks, you'll start to kind of a lot more of it will start to make sense. Okay, and so actually for this homework assignment, I would actually recommend that you look at it beforehand, and so just kind of read through the questions, kind of what I'm asking for. And then look for that information to be covered in the lectures. And I think you'll have a much better experience with the homework assignment, rather than, just kind of waiting until after we cover it, then looking back and seeing, what you need. So, today's an exception, of course, because, I don't expect everyone to pull it up right now and look over it in 10 seconds. But, after today, I would definitely recommend looking at the homework assignment, seeing what's asked, and then kind of use that as your guide to kind of, picking out what's important in the next few lectures. Okay. All right, and so that's all my announcements. And so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, and so the topic for this week is gait biomechanics. Okay, and that's GAIT. Okay. And so just, first as a definition, if you've never seen the term gait before, all gait really refers to is just kind of the act of walking or running. So kind of self-propulsion, or how a living being transports itself from point A to point B. Okay? So I've actually heard that there are stores out there, and there's one in Brea actually, I think called Snail Space. I don't know if they're still there, but they offer a service where they can analyze your gait. And so what that means basically is that they're going to have you walk and run on a treadmill, and they're going to look at a lot of your biomechanics, biometrics, and use that information to sell you a shoe. And so that's basically what it means. Okay. And so of course humans, we're not the only animals here that oh nice. And so the humans were not the only animals here on Earth that that transport ourselves through walking. And so if you think about a lot of our animal companions like dogs, cats, even bigger animals, most of those animals will walk, except humans are just one of the only ones that walk on 2 feet. Okay, and so we're going to, of course, we're going to be focusing on that. But actually, in a couple of weeks, we're going to talk about the final project. And a popular topic for the final project is actually analyzing, things like how animals move. So I know in the past people have done like dogs, they've done birds as well, and so this all kind of falls in that category. But for the lectures, we're going to focus just on humans. Okay. All right, and so I will say that this is a little bit of an unusual place to begin with human dynamics, because it is fairly specialized. And so, a lot of the terms that we're going to cover and a lot of the concepts, they're specific just to gait. But I want to start with this because, walking and running, I think, is something that, most people are very experienced with. At the very least, we can observe people walking and running. And so I think it's kind of serves as a nice kind of starting point for kind of defining just kind of where we're going to go over the next few weeks. Okay. Because we're going to talk about a lot of things like motion kinematics, and so that's going to be a big topic, as we go through the next few weeks. Just measuring motion, how do we quantify it, in action? Things like modeling, and so how do we come up with some mathematical models, physical models for motion? Because in truth, human motion is really complex if you consider all the different muscles and all the different degrees of freedom involved. And so to do any kind of analysis, a lot of times you're going to have to do some kind of simplified model or some kind of computational model. And so we'll talk about that. And so I think just a lot of those concepts, just if we kind of start with something concrete, then I think it just makes a lot of the next few weeks a lot easier. And so that's kind of why I kind of made this choice to start with this. Okay. Okay. And so, the main thing is that when we think of walking, we think of running, we think of those as like very, very basic actions, right? And so, like you think of a baby, right? When they make their first step, that's a big deal. But for adults or for kids, walking is something that's so basic, right? It's like we don't even think about it when we're doing it. But if you really kind of stop to kind of examine walking, you'll see that it's actually a very, very complex motion. Because not only does it have a lot of degrees of freedom, right? And so you have all the different joints and all the different bones in your lower body, but it also requires the coordination of literally like almost 100 different muscles working together to form one coordinated action. Okay. And if you ever need evidence, just look up YouTube videos of walking robots, or just ask anyone that's worked in robotics, if it's easy to develop a robot that walks naturally. And everyone will tell you that it's one of the hardest things. We've come a long way now. And so if you look at a lot of videos, and so let's say that I know the company Boston Dynamic posts a lot of videos. And so what they've been able to do with robotics is amazing. So we've come a long way. But if for a lot of those videos, like the Boston Dynamics videos, that's literally decades of research that went into that. And so what our body does kind of on a normal basis is definitely not easy to replicate. And so and I hope by the time we finish this unit, you kind of get an appreciation for that, because it is really amazing. And so just the fact that you can get out of your chair, get out of bed, and just walk to the other side of the room without even really thinking about it is incredible. And so that's kind of one of the amazing things about our body. Okay. And so we're going to talk about both walking and running, but we'll save running for Thursday. And so today we're going to focus on walking. Okay. All right. And so when we talk about walking, we talk about their kind of various stages and various events that happen throughout, a typical gait cycle. Okay. And so when I talk about gait cycle, what I'm talking about is kind of one full motion of the foot, starting from when the foot makes contact to when the foot's in the air to when the foot is makes contact again. Okay? Okay. And so I'm going to draw kind of a reel here for you to kind of show, all the various events. Okay. And so there's 6 main events, or there's 5, but the 6th one is just a repeat. And so I'm going to draw the pictures for you. Okay. And so I'm going to focus just on one foot. And so we'll imagine it's the right foot. And so let me go ahead and draw the 6 stick figures, and then I'll draw the foot in action. Okay. So what I'm going to draw now, it's going to be weird because I'm drawing all one-footed people, but I'm going to use a different color for the And I know this person has like legs longer than their whole body, but it's easier to kind of illustrate that way. Okay. All right. And so the first event, and so what we consider the beginning of the gait cycle is when your foot first makes contact with the ground. So this is kind of heel down in the gait cycle. Okay. And so we're going to define that like this. Okay. And so we'll call this event foot contact. Okay. right? And so, typically when you walk, you kind of lead with your heel and then you touch down with your heel. And so the next event is when your toes kind of come down and touch the ground as well. So we call this flat foot. Right, and then as your foot kind of makes contact, your full foot's on the ground, you're going to start to push off on your toes. And then as you push off on your toes, your heel is going to come off. And so the next event is heel off. Okay. And so that's when you're kind of using that foot to kind of propel you forward. Then, at a certain point, you're going to push off and your toes are going to come off. Okay. Okay. Right, then once your toe kind of leaves the ground, then your other foot's going to be in full contact. And so then you kind of reach what's called maximum knee flexion. And so your foot's going to be kind of flexed like this, or your leg's going to be flexed. Okay. And then eventually, once your knee is flexed, then that allows your foot to kind of swing forward again. And then eventually you're going to repeat the process. Okay, so once the leg kind of swings over, you're going to repeat the process and then come back to here. Okay, so that's the full gait cycle. So, heel down, flat foot, toe off, knee flexion, and then back to heel down. Okay. All right. And so I'm going to use this diagram to show different stages of the gait cycle. Okay. Okay, so this portion of the gait cycle right here, I want to highlight the first three actions because this is when your foot is in contact with the ground, okay? And so we call this the stance phase. And the stance phase for typical walking lasts about 60% of the time. Okay. And then once your foot is in the air, we call this the swing phase. That's when your foot is kind of swinging. It's not on the ground, so it's kind of swinging forward. And this takes up 40% of the time. You'll notice that the stance, for walking at least, the stance phase is longer than the swing phase. And so there's, your foot or your leg spends a longer proportion of the gait cycle on the ground. And so, of course, there's going to be an overlap. And so during this kind of short time right here, like right there, okay? And so kind of at the tail end of the stance phase for one foot, but at the beginning of the stance phase for another, we call that double support. Okay. And during double support, both of your feet are on the ground. Okay. And double support is approximately 10% of the gait cycle. Okay. And so there's a double support for this one. And then if you quantify it, there's kind of another double support phase over here too. But that's kind of, that's if we track the left foot, okay? And so overall, you spend about 20% of the gait cycle in double support. Okay, so 10% for, when one foot is just about to leave the ground, and then 10% for the other foot, okay? And so this diagram right here, I should have written it. This diagram is for the right foot. Right leg. as indicated by the colors. All right, so today, it's going to be a little bit similar to one of our first lectures. So I'm going to throw a bunch of terms at you, and so hopefully these terms are a little bit easier to pick up than the names of bones and muscles. But there are quite a few terms, but hopefully they're not too difficult. All right, any questions on this so far? All right, and so now that we've kind of looked and seen what the full gait cycle looks like and kind of what the leg is doing in each phase, let's define some additional terms here to describe the motion. Okay. And so let's give definitions to the first two words that I've given. So first, let's define stance phase. So the stance phase is when the foot is in contact with the ground. Next, we have the swing phase. And so the swing phase occurs when the foot is off the ground. Okay. And just for some completeness, I know I defined it up there, but double support is when both feet are on the ground. Okay, so those are the definitions for the different phases that you see in the gait diagram. Okay, we also have some other definitions we can define that define, I guess you can call it the walking performance. It's not that walking is performative in any way, but I don't know what else to call it. Okay. First, we have the step length. And so the step length, just like it sounds, it's the length of kind of one full step. Okay. Right, but we should be more precise, and so we can define the step length as the distance along the line of progression between the same point on two consecutive footprints. Okay. Then we have the stride length. And so the stride length is the distance traveled in two consecutive footprints or in one full gait cycle. And so when your foot kind of leaves the ground and comes back and then leaves the ground again, the stride length is the distance traveled in that one gait cycle. And just as a quick aside, step length and stride length, of course, are related. And so to compute them, we have stride length. Stride length is equal to the sum of the left step length and the right step length. Okay. Okay. So, you just take, how long your left step was, and then how long your right step was, and that's how far you travel in one gait cycle. In other words, a stride. Okay. Okay. Next definition is the step frequency or the cadence. And so the step frequency is the rate at which foot contact events occur. Okay, and then we also have the stride frequency. And so the stride frequency is the rate at which gait cycles complete. Okay. And then we have a formula here that relates the two. And so, usually you have two steps in a gait cycle. And so generally the step frequency or the cadence is 2 times greater than the stride frequency. Okay. Okay. All right, and then we finally we have the walking speed. And so the walking speed is simply just the velocity of the forward motion of the walking. Okay. Okay. And then using the last few definitions here, we can define the walking speed in a couple different ways. On the one hand, we can use the step length and the step frequency. And so just multiply the two. Okay. And so if you know how long the steps are, you can just multiply it by how quickly they occur. That's going to give you the walking speed. Another way to compute this is to use the stride quantities. And so we have stride length multiplied by stride frequency. So a lot of vocab, so a lot of different terms, but hopefully, again, they're more or less straightforward. Okay, I think the difficult thing with these terms is just getting step and stride confused, and so make sure you have that that difference in your head. So the step is just kind of just for one foot. A stride is for an entire gait cycle. So just remember that there's 2 steps in a stride. Okay. Any questions on this? Okay. All right, and so that's some definitions. And so now let's start talking about the dynamics of walking. Okay. And so first thing we're going to talk about, and you've kind of seen this in a few of the problems already, is the ground reaction forces. Okay. So ground reaction forces in general are going to be really important for human motion. because by ourselves, just the human body, we're unable to propel ourselves forward. Okay, and so a common saying nowadays is to kind of pull yourself up by your bootstraps. Well, it's literally impossible to do that because if you consider yourself kind of a dynamic system, you can't use. It's impossible to use any kind of internal forces to actually give yourself any motion. Okay, and so if you literally try to like take your belt and pull yourself up, you're just going to give yourself a wedgie, and there's no way you can actually pull yourself up. Okay, and so our interactions with the environment is crucial to human motion because that's the only way we can actually move ourselves forward. Okay, and so in walking, on running as well, something that's just as important as what the body's doing is the reaction forces that the ground is putting on our bodies as well. Okay. Okay. So let me start by saying that to move the center of mass, an object, and so basically to do any kind of motion at all, you need to be acted on by an external force. Okay? And so typically the way that we generate that external force in walking is we use our muscles and we exert a force onto the ground, and then the ground exerts a reaction force back to us, and then that reaction force is what propels us forward. Okay. So if you actually wanted to measure, or you actually wanted to compute, the act of the human body moving forward, you actually need to measure what those external forces are. Okay, of course, it is going to be important, and it is useful to measure what the muscles are doing. But in terms of actually generating motion, that can only be done by external forces. Okay. And so because of this, a lot of research has been done in terms of, how do we best measure these ground reaction forces? How do we characterize them? And, is there anything important that we can draw from these? Okay. All right. And so, to measure these, the main way that we do this in a lab is through what's called a force plate. Okay. Okay. And so a force plate is basically like a scale. And so, in theory, it's not that much different than the scale you probably have in your bathroom that tells you you're overweight every single day. But of course, it's a little bit more sophisticated because if you think about the scale in your bathroom, it takes your scale, a couple seconds to tell you your weight. Okay. And so force plate is designed to act much quicker. So, basically, as soon as you step on the plate, as soon as you apply any force, it's going to tell you what that force is. Okay. And the other thing that a force plate can do is that it can not only measure force in the vertical direction, it can measure forces in the horizontal direction as well. Okay. And so visually, you know, it might look something like this. And so let's say that here's the ground. Here is the foot. Okay. Okay. And so let's say that this is kind of right when your toe is about to leave the ground. And so this is kind of maximum push off here. Okay. And so to oppose this force, okay, so your muscles are basically driving your foot into the ground. And so that's going to put a vertical force down. And then in response, you know, the ground is going to put a force, you know, in this direction. And so, of course, there's going to be a vertical component to the ground reaction force because that's supporting your weight. But because, you know, because of friction and the fact that your foot is kind of pushing into the ground to move you forward, there's going to be some horizontal component to the ground reaction force as well. Okay? So that's why I kind of drew it off to the side of it because, you know, the ground reaction force has multiple components. All right, so let's let me draw for you kind of the typical ground reaction forces that you can expect. And I'm going to split it into two components. And so I'm going to have one component in the vertical direction and then another component in the horizontal direction, in other words, the forward direction. Okay. Okay. So it looks something like this. Okay, and so on the x-axis, we're going to have time, and on the y-axis here, we're going to have force. And so, you know, the units for force can be newtons or, you know, could be pounds or anything like that. Okay. Let me draw the vertical reaction forces first. Okay. And so the progression of this graph kind of follows the same gait cycle that I drew up here. Okay. And so the beginning of the graph is going to be foot contact. And then we're going to follow the ground reaction forces all through, you know, the various stages of stance. Okay. And so I'm not going to plot the ground reaction forces for swing because, you know, when the foot is swinging off the ground, then it's not going to have any, you know, ground reaction forces. Okay. And so we're going to start with foot contact. And of course, in the middle here, we're going to have foot flat. And at the end, we're going to have toe right when the toe comes off. All right, so let's do the horizontal, the vertical reaction forces first. Okay? And so the vertical reaction forces kind of looks like this. Okay, so kind of has this double peak behavior. Okay. And then from there, let me draw the horizontal reaction force. So the horizontal reaction force kind of starts down, and then it comes up, and then it comes down again. You can find a much prettier picture in the well, first of all, in the textbook. And so we're switching over textbooks too. I don't think I mentioned that. And so I'm switching textbooks to the DELP textbook. And so the textbook is called Biomechanics of Motion. And so you'll find this this figure in there as well. Okay, so there's kind of a lot to unpack here. And so let me kind of spend some time you know, talking about the essential features of this. Okay. Right, so first let's explain the double peaks, okay? Because the double peaks is a pretty defining characteristic, okay? And so the first peak occurs, you know, basically when the foot makes contact, okay? And so that's basically the impact force of your foot coming down from the swing and the ground kind of reacting to that. Okay. Okay. Right. So the first peak is just a cushion, and so it's almost like a brake. Let's think of it like that. Okay. The second peak occurs when you're actually pushing off your toe, and so when you're pushing off your toe, you're trying to, you're using that to kind of propel yourself forward, and so as you kind of drive your toe into the ground, then that produces another peak in the vertical reaction force. Okay. Okay. And so that's kind of what's going on in the vertical reaction forces. Okay, so that explains the two peaks. For the horizontal reaction forces, we kind of have we have a negative portion and the positive portion. Okay. So first, let's explain what's going on with the negative horizontal reaction forces. Okay. And so a negative force obviously means that the force is pointing backwards. Okay? And so during that first part of the gait cycle, when your heel first makes contact with the ground, that your heel is actually kind of acting like a brake. So that's actually slowing your motion down and kind of slowing you down, make you go backwards. Okay? Meanwhile, the positive portion of the horizontal reaction force, that comes from your toe. Okay, and so the positive portion of the horizontal reaction forces kind of corresponds to the second peak. Okay, so as your toe is driven into the ground, that's going to provide a positive force that pushes you forward. Okay. Okay. All right, and so hopefully that kind of explains the various trends. Okay. Oh, just a couple more things. These are kind of minor points, but one thing you'll notice with the horizontal reaction forces is that they actually sum to zero. So if you were to actually sum up all these quantities here, or if you were to take the integral, they actually sum up to zero, which may seem counterintuitive, right? Like, how can you have forward motion if your horizontal forces all sum to zero? And the reason for that is that this kind of assumes you're walking at a steady state. And so if your velocity is constant, then you're not accelerating, at least not in the mean, then your horizontal forces are going to sum to zero. Okay. On the other hand, your vertical forces, they obviously don't sum to zero. And so if you integrate that, then that's going to be non-zero. And the reason for that is because the vertical reactions are there to counteract gravity. And so because gravity is always producing a force, then there always has to be a ground reaction force non-zero to counteract that gravity. Yeah.
So if you were to be accelerating, that would not seem to zero?
Exactly. And so if you were accelerating, then this curve would be modified here, where you would probably have a higher portion there on the toe. Yeah, but this graph right now assumes steady state walking. Yeah, question? Okay. Any other questions on this graph here? Great. All right, and so over the next few weeks, we're going to see quite a lot of graphs like this. And so graphs like this kind of fall in the category of kinematics. Okay, so kinematics are very important to human dynamics because these are basically ways that we can track and we can quantify and we can graph, what the motion looks like. Okay, and so we're going to be seeing lots of graphs like this. Okay. But this graph in particular, we're actually not done with this yet, and so we can work on this a bit more. Okay. Because now that we have the forces, okay, and we know what the external forces that are acting on the body as a function of time. Or in theory, we can get them. So as long as you have a force plate, you can get a graph like this. What you can do is you can then integrate those forces to obtain things like velocity and position. Okay? Let me show you what I mean. And so, what we have obtained in the graphs up there is that we know the external x direction force or the external horizontal force as a function of time. Okay. And we know the external vertical force as a function of time as well. Okay. So we basically just measure these. Okay. And so what we can do is we can make use of the fact that F is equal to m times a. Okay. And so the horizontal force is going to be equal to m times a in the x direction, and the vertical force is going to be m times a in the y direction. Okay. And we can just integrate these in order to obtain the velocity. Okay. And so, for instance, if we take the horizontal force, we divide by m. Okay. So we have 1 over m on this side, and we integrate the force dt. Okay. And then for y, we can say that ay is equal to 1 over m times the integral of fy t dt. Okay. And we actually have to subtract gravity as well. Okay. Gravity is part of the process here. Okay. Because remember, there is gravity acting on this. So we're basically performing a free body diagram, and we're getting the force saying it equal to a. Okay. Oh, I'm sorry. If we perform the integral, then these should be just velocities here. Because the integral of acceleration is velocity. So I kind of combined two steps. And so what I did from the previous equations was I divided by a, and so that solved for the accelerations. And then from the accelerations, I performed an integral, and then by performing an integral, then we get the velocity. Okay, so I kind of did two steps at once. Okay. All right, and so we know that once we have velocity, we can integrate one more time to get position. And so the position in the x direction, we're going to integrate with respect to time one more time. Okay, so we're going to integrate twice. Same thing for the y direction. Okay. 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 And of course, these are useful. And so, based on the ground reaction forces, we can measure and we can compute, the motion of the human body. Okay. And so, of course, we're assuming that the body is just a particle here, but that's a start. Okay. In particular, let me take the horizontal velocity as well as the vertical positions. Okay. And I'm going to use these to compute some energy. In particular, I'm going to compute two different kinds of energy. So the first type of energy I'm going to compute is a kinetic energy. Okay. And so if you remember from your physics class, kinetic energy is 1/2 times the mass times the velocity squared. And so in particular for walking, we're mostly interested in the forward velocity. And so that's why I'm just going to take the Vx. Okay. And the other energy that I'm going to compute here is the gravitational potential energy. Okay. And so gravitational potential energy is just the mass times the acceleration due to gravity times its height. Okay. And so we have mass times gravity. And the height in this case is going to be y as a function of t. Right, and so we can compute those energies, just based purely off the kinematics, and so just purely off the velocity and the position. Okay, and so why am I computing these? And so we've departed quite a bit from our ground reaction forces, and so if you compute these and you plot them for a typical person that's walking, what you see is actually some very interesting behavior. Okay. And so let me show you the results of what happens if you take the ground reaction forces for a typical gait cycle, you compute the acceleration, the velocities, and the positions, and then you use those to plot the energies. Okay, let me show you what it looks like. Okay, so on the x-axis here, we're going to have time. On the y-axis here, we're going to have energy. And so I'm going to draw for you the kinetic energy and the potential energy on the same graph. Okay. All right, so let's start with the potential energy. Okay. And so you don't have to be super precise with this. But what you should see is that the potential energy is going to go kind of up and down like this. Okay? And so that tells you that as you're walking, you kind of have this kind of bobbing motion. So, as you walk and kind of as you transition from stance to double support swing, then your center of mass kind of goes up and down. Okay. And so next time you see someone kind of walking down the hallway, kind of look at their body, and you'll see that it kind of goes up and down. Okay. So that's the potential energy. Pick a color that's easy to see. All right, and then on the other hand, if you compute the kinetic energy, it looks something like this. Right, and so your speed isn't constant when you're walking too, right? And so depending on if you're pushing off or whether your foot's coming down, right? And so your speed kind of goes up and down as you're walking as well. And so that's of course going to be reflected in the kinetic energy. Okay? And so, both your vertical position and your forward speed kind of have some variation to it as you're walking. Okay? So there's kind of, it almost looks oscillatory in nature. It's not exactly, I know I kind of drew it as if it were a sine wave because that's the best I can do, but it looks very oscillatory. Okay. Okay. And so that's the first observation that you should make from this is that your speed isn't constant and your center of gravity isn't constant either. You kind of go up and down. Okay. If you want kind of the ultimate test with this, try filling up a glass of water and try walking at your normal pace and seeing if you spill water on your feet. And I will guarantee you walk normally, you will spill water on your feet because not only is your body kind of going up and down, but your speed is kind of varying, front and back as well. And so you have some kind of acceleration. That's why when you walk, the water kind of, tips over. All right, so that's the first observation. The other observation that you can make from this is that the kinetic energy and potential energy are never peaking at the same time. In fact, what you see is that they're perfectly out of phase with each other. Okay. So when one is peaking, the other one is at its lowest. And when the other one's at its lowest, then the other one is peaking, right? And so you kind of have this, they're kind of trading off, right? They're trading off in such that, the sum of their energies is roughly constant throughout the Gait cycle. It almost kind of makes it seem like, as you're walking, you're at any given time, at a given point in the Gait cycle or throughout a Gait cycle, all you're really doing is just kind of exchanging potential energy for kinetic energy, potential for kinetic for potential. Okay? And so there's this constant kind of exchange between the two. Okay. And so it's for this reason that walking is mostly a passive activity. Okay, and so I know that's probably the last thing you want to hear when you're walking around Disneyland for like 8 hours and your feet are killing you. Okay, last thing you want to hear is that walking is passive because it doesn't feel like it. But when you compare it to running, and we'll talk about running on Thursday, walking is mostly passive. And so your body actually isn't doing all too much. The most work that it's doing is just kind of supporting your weight. But in terms of actually providing forward motion, your muscles actually aren't really doing all that much. Okay? And so because of this, there's actually a very elegant and very interesting analog for walking that scientists have developed. Well, they didn't develop it, but they kind of noticed it, and that's a pendulum. Okay. And so if you look at a pendulum, okay, so pendulum, you have a weight at the end of a string, okay? And so if you track the motion of the pendulum, right? And so the pendulum has different stages as well. And so, we can say here that, it starts out maybe here, and then it's going to swing down, and so come down to its resting position. Okay? and then it's going to come up here. Okay. If you think about how a pendulum behaves, it's very similar to what we see from walking. Because at the maximum height, and so kind of at the sides here, okay, basically when the pendulum reaches its maximum height, it's not moving, right? And so there's kind of a brief moment in time where the kinetic energy of that pendulum is approximately 0, okay? And so it's at that time that the potential energy of the pendulum is the highest, because that's its highest point off the ground. Okay? Whereas if you compare that to when the pendulum's at the lowest point, okay? And so when the pendulum's at the lowest point, its velocity is the highest, and so that means its kinetic energy is the highest, but its height is the lowest. Okay. And so, if you watch a pendulum and you have a good one that's relatively well greased, right? And you pull it back, the pendulum can go, it almost seems like forever, because you basically just have this exchange between potential energy, kinetic energy, potential energy, kinetic energy, potential energy, kinetic. Okay. The only thing that really stops it is some air resistance, but that usually takes a long time to do. Okay. And so, what scientists have been able to observe with walking is that it's very similar. So you just have this exchange: potential kinetic, potential kinetic, potential kinetic. Okay. And so that's kind of led to a lot of a lot more simplified models for walking, that we're going to talk about in the last part of the class today. All right. Any questions on this? Okay. All right, so let's talk about some simplified models for walking. So we'll call these the ballistic walking models. Okay. All right. And so, the first word I want to kind of draw your attention to is the word model. Okay, and so it's probably the word that kind of drew your attention the least once I first wrote this. But a model is simply just a representation of reality. Okay, and so like I mentioned at the beginning today, if you were to really analyze walking, you would see that it's very complex. It's you have probably a dozen muscles that are working together. You have all these bones and all these joints moving at the same time. It's an ordeal, and it's hard to really quantify that in kind of in kind of deep precision. And so to kind of simplify analysis, all the time, we're coming up with these models in our brain, which are basically just simplified versions or simplified representations of a real event. Okay? Okay. And the reason we make models is to make analysis easier, basically. So it's a lot easier to analyze a model than it is to analyze the real thing most of the time. And so kind of based on that, and kind of based on the fact that walking shares a lot of similarities with the pendulum, a lot of the really early models for walking use that idea. And so the one that kind of gained a lot of traction early on was something called the inverted pendulum. Okay. Okay. And it looks just like a pendulum, just turned on its head. Okay. And so just like the pendulum, we have a mass that's at the end of, well, this time it's at the end of a stick. Otherwise, the pendulum would fall apart. Okay. And so the stick here has a length of L. Okay. And so the idea with the inverted pendulum is that this would be a simplified model for a single leg that's in the stance phase. Okay. Okay. And so, first thing you probably said when you saw this is that how can this be a model for walking? And so, imagine that the mass M here, this is kind of attached at your hip. And so this would kind of represent the mass of, the entire upper body. And then the pendulum arm, that's the leg, okay? And so you might still be confused. And so, how is this a model for walking if the foot, which is here, okay? In order to have a pendulum, the foot has to be fixed to the ground, okay? And it is right here too. And so, I want to kind of emphasize this is a very simple model. So the idea is to just kind of simplify and kind of track the motion of the leg in a single stance phase, okay? But the pendulum doesn't actually move, so it doesn't actually move forward. The idea is just to, can we replicate, maybe this energy behavior right here, for just a single leg, okay? And so, this was kind of the first iteration for this model. There have been others that have been developed, from this. Okay. And so, in particular, one advancement to this is to add the swinging leg. Okay. So, if this is the stance leg right here, we can add the swinging one. And so if this is the inverted pendulum here, we have the mass that's up here. Okay. Right. If you were to add an additional limb here, so let's say that this is the swing limb. And of course, what we model it as here as kind of a double normal pendulum. So there's going to be a mass at the end of here as well. It's going to be a smaller mass because that mass just represents the mass of the foot. Okay. And so this is kind of one way that we can extend that inverted pendulum. We're not going to talk too much about this just because then that gets into too many details. But the reason I kind of bring this up is to kind of show you what this model represents. Because I think it's a bit hard to go from pendulum to gait cycle. Okay. But I will say that even for this very simplified model right here, what scientists have found is that if you kind of set the conditions just right for this model, and so you kind of start it in the right position and you kind of push it in the right way, this really simplified model actually can replicate, an action like a pretty realistic looking step, without any actuators. And so, there's no motors here, there's no actuators here. It's all purely passive. But if you kind of set it off in the right way, right? And so you basically, maybe the pendulum starts over here, okay? And then let's say you kind of push it at just the right speed. What you'll observe is that the swing leg will kind of do the natural action. So the swing leg will kind of come up, it'll flex, and then as it comes down, the swing leg will kind of make contact with the ground just like that. Okay. And so even though it's a very simplified model, there are ways to get it to do realistic behavior, which is pretty cool. But for the purpose of analysis, just for simplicity's sake, I'm going to focus back on just the pendulum here itself. But I just wanted to show you that this model is legit. It actually does work. Okay. And so from the inverted pendulum, okay. Right. And so from the inverted pendulum, we can do some analysis on this. We can do some computations in order to learn some important information about walking. Okay. Okay. In particular, let's look at the situation when the pendulum is at its maximum velocity. Okay. And so we know that the pendulum reaches max velocity when the string is at its most vertical. Okay. So here we have our inverted pendulum. It's moving to the right with the velocity v. The length of the pendulum is still L. Okay. And so when a pendulum is in this position right here, we know that there has to be some kind of centripetal force that kind of holds it together, right? And so even though the velocity is pointing to to the right, there has to be a centripetal force here, because the pendulum is undergoing circular motion. Okay? And so from physics or from rotational physics, we know that the centripetal force is equal to the mass of the object multiplied by its velocity squared divided by the distance from the rotation center. Okay, and so these are all quantities that we know. Okay, because we know the mass, we know the velocity, and we know the distance from the rotation center. Okay. And so if the pendulum were to have this motion here, there has to be some kind of external force that provides this force. Okay. And for an inverted pendulum like this, the force that is acting in that centripetal direction is the gravity force. So we have the mass times the gravity. Okay. And so we have this relationship right here. And so we have the mass times the velocity squared divided by the length. It's equal to the mass times the gravity. Okay. Let's solve this for the velocity. Okay. And so if we solve this for v, then what we're going to see is that the mass here is going to cancel out. Okay. The L is going to come over to the other side. And then we're going to take the square root of both sides. And so we get the velocity is equal to square root of gravity times the length. And so why is this result significant? And so we know that when we're walking, we kind of have this exchange between kinetic and potential energy. Okay? So the muscles themselves in the leg are actually not really doing much. They're just supporting the leg. Okay. And so with that in mind, that kind of puts an upper limit, or kind of puts a cap on the maximum speed that we can go when we're walking. Okay. And so using this inverted pendulum model, we can see that the maximum speed, depends on a couple of things. So it depends on the gravity, and it depends on the length of the leg. Okay. Okay. Right, and so that means if you're a longer-legged person, so if you're taller than me, which is not hard to do, you're going to have a much higher walking speed than me. Okay, and that makes sense, right? And so we kind of observe that naturally. And so people that are taller, longer legs, they can just walk a lot faster than the people that are short legs. Okay, I think the surprising one here is gravity, and so your walking speed depends on gravity. And we've actually confirmed this as well. And so if you look at kind of very early, videos of astronauts walking on the moon, kind of the stereotype that you see is that the astronauts are walking super slow, right? And the reason for that is because the gravity is much weaker on the moon. And so, that's going to put a big limit on how quickly you can walk. Eventually, we learned that it's efficient to just, hop on the moon. And so it's more efficient just to hop around rather than walk. But if you try to walk as you did on Earth, you're going to have a much harder time doing that because of gravity. Okay. Right, and the same goes when you're walking underwater too. And so it's not quite the same, but when you're walking underwater, you have a much higher buoyant force that kind of pushes you upward. And so your effective gravity is lower there too. And so when you're walking underwater, it's a lot slower because your effective gravity is a lot less. Okay. And so even from this simple pendulum model, we were able to obtain this kind of really interesting result that our walking speed depends on gravity and the leg length. Okay. All right. Any questions on this? Okay. All right. And so that's all the time we have for today. And so on Thursday we'll pick this up and we'll start talking about running. Okay. And so thank you guys for coming today. Remember, on Thursday, I plan to have your midterms graded. And so if you want to come to the lecture, I should have them ready by then. Okay. So hope you guys enjoy the rest of your evening, and I will see you guys on Thursday. Yeah.
One question.
Oh, yeah.
So, is there a way to find the average?
Yeah. And so, it's, I think the hard part is actually measuring the weight of the arm.
Okay.
Because, if you were to go off by densities, you have to consider the density of the bone, the density of the muscles and all that stuff.
Most of the time.
Ah, okay.
Yeah,
Okay.
so we're trying to find the appropriate motor to
Yeah.
drive like it's called the shoulder joint. It's a big joint.
Yeah.
I guess when you find the motor like to find the force of the shoulder.
Yeah.
And also I guess the elbow, what we call it.
Yeah.
So if we have the weight, we have length, we have approximate like position, we have like the highest I'd say moment.
Yeah.
Biggest moment. Yeah, that's another question. Should we use like the position which has like the largest moment in order to figure out the
Yeah. And so I would definitely, the largest moment is going to be when the arm is fully extended. And so I would use that and, probably in the horizontal position.
Yeah. And
you would analyze it the exact same way we did before with the static analysis. And so you'd measure kind of the weights and kind of what the moment arms are. And then, instead of a muscle force there, you would just compute just the raw moment that you would need at the joint there to move it. And then that will give you your knowledge. But I will say that, remember that's a static position. And so when you're in motion, you need a higher moment than you're actually force motion.
Gotcha.
And so you probably need a factor of safety in there. I don't know what's the I would say at least 2, just to make sure that you can, but that's how.
Yeah, we're using this included because it has like very little backlash on it. Yeah, so just like a little arm. Yeah, thank you.
Yeah.